All right, I think this is a good time to start. Welcome everyone. Thank you so much for coming. This webinar was the brainchild of Dr. Katie Mills, who is the director of the Viterbi K-12 Center at USC. I am Dr. Shaama Sharada. I am an assistant professor in the Department of Chemical Engineering and Material Science with a joint department in the Department of Chemistry. So I have had an ongoing partnership with the Hawthorne Math and Science Academy, particularly with Ms. Meredith Brandon. She virtually visited our group over the summer. She worked with my graduate student, Kareesa Kron, and came up with a nice lesson plan on greenhouse gases using some of the modeling tools that we use on a regular basis in our research. So we thought this would be a great way, particularly with things going virtual, to be able to use some of the visualization tools that we use. And I will let Kareesa and Meredith take over because they did all of this fantastic work of putting together a very nice comprehensive lesson plan. So take it away, you guys.
Thank you, Dr. Sharada. Like Dr. Sharada mentioned, my name's Meredith Brandon. I'm an environmental science teacher at Hawthorne Math and Science Academy. I teach a on-level environmental science class and also AP Environmental Science. Before we get started, I just wanted to remind you, as I'm sure you all do with your students, about just some Zoom etiquette. If you're not speaking, please make sure that you're on mute. I know sometimes we can have some background noises or things, so just be mindful of being on mute when you're not speaking. It's always nice to see faces, so we can put them to names and voices. So if you are able to, please have your camera on. And then, of course, you can use the chat feature or the raise hand feature if you have a question or something you'd like to voice as we go through our presentation. But thank you all for coming, and we're looking forward to presenting our lesson to you.
And so Dr. Sharada might want to talk a little bit more about this, but I like to introduce myself. And so my name is Kareesa Kron. I'm a third-year PhD student in chemical engineering, and both my undergraduate and graduate research has been computational chemistry. So I've used programs like this and, this program and one other program to model chemical compounds for a variety of purposes. And as chemical researchers, these tools allow us to do some of the quantum chemistry and math we need to do in order to accurately describe the motions and the attractions and the repulsions of electrons and calculate the properties of chemicals so that we can both compare to experimental papers and also develop predictive models. And so we're teaching you guys today how to use IQMol. Some of you may have downloaded it, but we're going to talk through the download and make sure that everyone's sort of on the same page. And the goal of this lesson and this collaboration was to use this sort of research-ready program to help you guys teach students about like fundamental chemical properties and how those properties relate to larger scale processes like global warming. And so today we're going to go really in depth and look at what happens at a molecular level and how that can explain some of the things that we talk about in classes. And if you have a question at any point, we'd love to hear it. And sort of, we know a lot about these and we've spent a lot of time developing this lesson plan, so we might have oversights about its content. And so we really appreciate you guys participating and learning more about this lesson plan, and hopefully we can develop it and improve it further so that it really suits your needs and is easy for you to deploy and helpful for your high school students. And so that's kind of the overall goal of this collaboration. And so we really thank you guys for being here and would love your input. Let's see.
So when we first started developing this lesson, I teach AP Environmental Science, like I mentioned before, and we thought this fit in perfectly to, if you are familiar with the College Board course description, if anyone out there teaches AP Environmental, the last unit is on global change. And so it really fits in perfectly to this topic 9.3 on the greenhouse effect. And this goes for not just College Board, but for any class in which you're discussing global change, climate change, and greenhouse gases. And so not only does it cover all of the parts of that topic, but it also gets into some of the science practices which are outlined by College Board, specifically the data analysis and looking at data in tables and charts and being able to explain how the data has and illustrates environmental issues currently going on today. And then outside of College Board, if you teach just an on-level or a regular science course, whether it's chemistry, environmental science, this could even be applied to some biology classes. The alignment for the NGSS is under the Earth and Space Science, and particularly also within the global climate change, being able to look at this geoscience data through IQMol and using it as a representation model to make evidence-based forecasts, and we'll talk about how the students will make their forecast at the end of the lesson. So it covers, a lot of interpreting and analyzing data. We're talking about global climate change and also looking at stability and change of these molecules over time. And then it also can, directly relate into a chemistry course in terms of the energy that we'll be talking about with the molecules as well. So it does have broad alignment to both the College Board, the AP Environmental Science Standards, and the Next Generation Science Standards as well. So the lesson plan structure is done in 2 90-minute class periods. I personally teach block scheduling, so that's how we kind of developed this. It can obviously be done in a regular, if you meet students every day. It can be changed and made to suit your needs. It does not have to be specifically over 2 90-minute class periods, but that is how it is outlined. But you can break it up beyond that as well. There's 2 homework assignments that do come with the lesson, and everything is included in the Google Drive folder that you all have access to. There is one pre-class activity to have students do, which is that downloading and testing out IQMol and just a brief survey to get some background information. And of course, this lesson does allow for both individual and collaborative work between students. And is using combined experimental and computational activities to, like we said, teach and be able to explain in depth to students greenhouse gases. So you'll see on the left-hand part of the slide there, when you are in the Google Drive, the numbers kind of help you identify the order. You've got the lesson plan and the summary, and then it goes through the pre-class, the lesson, and the homework for each day. So hopefully it's organized in a way that is easy to use and understand for everyone.
So the first step of this is we'd like to know how many of you were able to download IQMol, and we're going to talk about kind of the first step of it. And so we would like to, yes. Okay, so there's a chat saying we can share the link, so I'll show that to you guys now. Let's see. So like I said, if you go to this website, there's this URL, which I'm going to share to you so that you can click on it. And then, oh, sorry, that was. So if you click on that URL, it takes you to this Drive folder here, which I'm going to view in an incognito tab so that I can see what you guys see. So I'm logged into one of my other Gmail accounts, so I don't have admin rights here. And so what you can see is that in this first lesson plan, this is the outline, which we're going to work through today. And in this lesson plan, in addition to listing the standards that we had before and some vocabulary your students may have never encountered, which we can talk about today, you have the link to the IQMol download, some descriptions of what the goals of the lesson plan are, and then in this folder you have a schedule which is based on those 90-minute periods. And that schedule walks you through the steps as we imagine you would go through the steps. But as Meredith mentioned, if, for example, you get to the first worksheet and you're like, oh, I think this would be perfect if I just changed this, I'm going to show you today how to copy our documents and edit them. And we'd love for you guys to do that and to make it your own. We just ask that you try to sort of reference the work at USC and also collaborate with us so that we can share the work that you do with other people, because we'd like this to be sort of a collaborative open source effort. And so we'll walk through this today in pretty good detail. We're not going to do everything because it is supposed to be 2 90-minute sessions. But what I'm going to talk about is the document that I sent you, which was this pre-class IQMol Quick Start. And the IQMol Quick Start shows you the website that you would use to download the program. And you have this binary downloads that shows up, and depending on whether you're a Mac or a Windows, you just click on the link and run the installer. And we helped someone earlier with some security issues, which makes sense, particularly if you're trying to download it on a school computer. But in theory, it should be a pretty quick, easy download and should launch to this IQMol window. And so was there anyone who wasn't able to get to the IQMol window who would like help from one of us right now before we get started with everything? Okay, cool. So I'm going to take that to mean that everyone either has it downloaded or is planning to work with other people in the group to get it downloaded, which one person said that that was the case for them. And so now the second step, I think, is a little less likely that you guys achieved, which is downloading the test input file and trying to submit it. And so I know a few of you didn't do it. So what I'm going to do is I'm going to walk you through this. And so in this pre-class 1 folder, which you should be able to see under the link I sent you, there's this test.imp file. So if you click on it and you download it, sorry, there's a lot of Zoom going on here. You can then, it should end up in your downloads folder of some kind. And then when you open IQMol, which I'm going to show you how to do. And stop me if you're having an issue at any of these steps as I go. So if you do File, Open, in this upper left-hand corner, you should be able in your downloads to see, and when it finishes downloading, you should see the like test.imp. I'm going to open a slightly different one so that you guys can just see what it looks like. We have a chat question. Formaldehyde. Yes. Okay, so let's see. If you open that input file, you guys, a molecule should appear on your screen. In theory. Can everybody get to this step? Okay, cool. I see some thumbs up. Okay, so the test.input here, I'll share one that you can use. Let's see. So these are, so in that drive folder, there's also all of these sample files, which I'll talk about today, but you can use this one instead of the test one if you'd like to. Okay, cool. Yeah, we're just using this to basically see if IQMol will submit the job is the goal. And so after you have it downloaded and open, we're going to go up to where it says calculation at the top of the bar and click on QChem setup. And you should have this window appear, which is the job that we're submitting. And so you can see at the top, there's this CO2 and then some information we're giving the program. And so, yes.
Can you slow down just a little bit? Let's see. Can you show the folder again where these test molecules were?
Yes.
I believe the test molecule is formaldehyde, not CO2, but I should point to the shared folder once again.
Yeah, so under greenhouse gas lesson plans, there's 1-_ pre-class 1, which you can open, and the test.imp is included here. And so you can right click on it and hit download. And it seems like mine isn't trying very hard to download it, but in theory yours should. It might be because I'm in an incognito fold drive so that I see the same thing as you guys. But I can open the other one. So.
And just a side note on the file naming convention, .inp is an input file, .out is an output file. We'll see that a lot, I guess.
Yeah, so this is what you guys should see.
Yeah.
Is everybody okay now? Sorry if I went too quickly.
I have CO2 in mine.
Okay, you can have either, it doesn't matter.
Okay.
Yeah, they both work. And we're gonna tell you how to prep these. I just wanna see, we need to group you based on who has the ability to submit. And so we're just doing this to prepare for the breakout rooms we're gonna do. And so now you have a molecule, and we're gonna go under calculation and QChem setup. So just to hover over that, it'll pop up, and then click on the QChem setup. Can everybody get here, or does someone need help? Oh, okay.
Can you repeat that one, please?
Yeah, cool. So if you hover over calculation, or you click on calculation, depending on your computer, there's this QC-Chem setup, which is the program that runs behind the scene. So if you imagine, IQMol is sort of the person you have to submit the orders to, but QChem is the program that runs the job. And so what we're doing is we're setting up a QChem job file. And because I sent you the input file, it's already set up. So all we want to know is if it works. And as we work through the lesson today, I'm going to teach you how to set this up, and we're going to build our own molecules. This is just to make sure that at least one person in each group can submit files. And something to note is that sometimes your ability to submit files depends on your internet connection. So since you're in Zoom, you have internet connection, but if your students are doing it, that could be an issue they run into. And so once we get to this window, we're going to hit submit in this lower right-hand corner. And it says that it's submitting it to the server QChem. And so rather than running this job on your computer or on a supercomputer, you're submitting it to these public QChem servers. And so we're going to hit submit. Yeah, okay. So the most common thing is what someone just posted in the chat, which is that it failed to connect. And so what we're curious is if there are someone who succeeds. So we'd like to know if there are any people who succeed. Hopefully there's a few. Okay.
I got a question. Mine doesn't have that little top section that yours has where it says calculations. I don't get that in mine.
Okay.
I just get the tabs. I don't get that file.
Okay. Would you like to
Edit
screen
display.
share? Okay, so this is a Mac, it seems like. So if you look in the upper left-hand corner of your screen, is there like a file bar on top somewhere that we can't see?
Okay.
And so if you have that file, to the left or to the right of file should be the calculation on the top. So it might not be attached to the window for a Mac.
No, I don't see it.
Top left
I just see what you see.
Click on the IQMol box and make sure that you're just
Yeah.
click anywhere on it. So it's kind of, it's the program that you're in. Like
Okay.
and yeah, okay, so now at the top, now that it's the program you're in, now you should see File, Edit, Display, Build, Calculation.
On the top left of the screen.
Okay, let me click on it.
Like on
No.
the top bar above the IQMol box. No?
I think we got it.
Okay.
No, I
I'm
don't
not able to
see
see it though.
If you could share your whole screen with us rather
Okay.
than IQMol.
Okay.
It's a little inconvenient, but it would make it easier. Sorry.
Yeah. So share the desktop, I guess.
Yeah.
Yes.
Okay.
There we go. So now if you click on IQMol again, anywhere, it doesn't matter.
Okay.
There, on the top left, you see File, Edit, Display, Build, Calculations.
Yeah,
Oh,
so click,
oh my God, this is what you meant.
Yes.
yeah.
Okay.
It's
I
And then
see.
do QChem setup, yeah. And then hit submit.
Got it. Okay.
Okay, so did anybody's work? Nobody's posted in the chat.
So it didn't work, right? So.
Yeah.
Okay.
Okay, we were kind of hoping some people's would work, but IQMol is a little fickle sometimes. Okay.
Let me see what I can do while you continue with the webinar.
Okay. So what we're going to do is we're going to have you prep the files and do everything prior to that step while Dr. Sharada tries to figure out sort of how to get one working. And then what we're going to do is we have the output files so we can show you what QChem would give you based on what we're doing. And so this, it seems a little intimidating to have something not work, but this is a pretty common issue with IQMol. And so we just wanted to see if any of you have one that like naturally does what it's supposed to, which is more uncommon than common. So what we're going to do now, let's move back to the presentation. Okay, so let me. Thanks for participating in that effort. Okay, so I think some of you had issues accessing the pre-check survey. It's now available, but I think it wasn't necessarily available. And so we asked the students to speculate about which greenhouse gases were, or which gases are greenhouse gases and what it means to be a greenhouse gas. And our motivation for asking these questions is that we wanted your students to get the chance to discover greenhouse gases rather than have to look them up and sort of learn about them online. And so we phrased it in this very open-ended way so that in class, they learn about the gases. And so ideally, some of you who responded said things like greenhouse gases are the gases that lead to global warming by absorbing energy or that sort of thing. And some of you mentioned CO2, methane, and those sorts of gases. And so I was wondering now if you guys could share out a few more that you think would be possible answers to the which gases are greenhouse gases. So you can either type them in the chat or unmute yourself. We're happy to hear what you guys think we should consider. Cool, yeah, we got water. That's a good one. Carbon dioxide, methane. Those are good. CFCs, ozone. Yeah. Those are good. Okay, so yeah, so ideally, something we expect students to also come up with are some of the ones you listed. Maybe someone who's like really experienced with pollution might come up with NO2, sort of the nitric oxides. And then another thing that we've included here is that some students might list nitrogen or oxygen if they've learned that that's what's in the atmosphere. And so not only do we include it as on the list of gases we explore for that reason, but we also use it to sort of show what makes something a greenhouse gas and what makes something not a greenhouse gas. And so because nitrogen and oxygen are such large components of the atmospheres, we want students to model them and learn why they're not greenhouse gases. And so we include them on the list here, even though you guys as educators probably wouldn't think to include them on a list of greenhouse gases. But we use them as sort of a foil versus the other ones. And you're right, Dimple, we could include ozone. One of the reasons we don't is that it's a little trickier for IQMol to model it sometimes. And so it could provide sort of more issues for the students than some of these, which are a little more straightforward. And so after we've had students sort of speculate about which gases are important, then what we do is we move to, we move to what's an in-class day one worksheet. And so in the chat right now, I'm going to share with you 2 links. One of these links is the cheat sheet, which part of is shown here on the bottom left. And the other is the student worksheet that they work through on the first day of class. And so I'm going to stop sharing this screen and I'm going to show you 2 things. So let's see, let it go. This, sorry. Okay, so for example, you guys will be interested in making these student worksheets for yourself. And so what you guys see when you go under the lesson plan, if you click on the link, you want to go to 2-in-class day 1. And when you click on it, all of these files open up for you. And the in-class day 1 worksheet here on the left is what you give your students. And you also give your students the IQMol cheat sheet. And what that is it's a simplification of the user guide for IQMol. And so if you click on it, for example, you can share this link with them, or you can make a copy of the file and share the link to that with them, depending on what you want to do. And I'll show you guys how to do that. But in here, it has the IQMol commands that you need to make the gases that we're talking about. And so in IQMol, there's that top bar that you see, and that top bar has all these little buttons you can press with different functionalities. And so this cheat sheet guide shows you or explains in words what each of these does. And so for example, this hand, which is what IQMol naturally loads you in as, allows you to grab and drag CO2 around. Whereas if you click on build, you can start attaching different elements, which you can find under the element button. And so after you click on build, you're like, okay, I want to add more carbons. And then you take and click and drag away from your current structure. And you can sort of do whatever you want with it. And if you're like, well, adding elements is cool, but I want to attach a whole functional group. So I want to attach an alcohol. For example, you can take and drag the alcohol off your structure. And so what this guide does is it tells you what you can do with the program, and it explains the buttons. And so we want students to have this on hand, and we want you guys to have this on hand while we try to build these gases, so that you're like, okay, I don't remember how to delete an atom because I just made this terrible looking structure. What should I do? And so it says you delete your atoms after you select them. And so then if you look up a line, it says, okay, use the select tool to click on the atoms. And so if I use this kind of magic wand, I can drag and delete a bunch of them, or I can click on individual ones. And then I can delete them using the red X. And so this guide is just supposed to help students interface with IQMol, and we're going to test out all these commands using this in-class day 1 worksheet. And so at the beginning of the first class, you hand out both the cheat sheet and this worksheet, which I'm going to share with you guys right now, in an editable format, because you'll notice if you try to edit this document, you can't do anything. And that's not helpful for your students. And so what you do is, rather than edit the source of the file, if you go back to your folder or you do it in the file, you can make a copy by right-clicking on the file, going down, hovering over make a copy, and clicking on make a copy. And when you do that, it will say, I've created this on your drive. Here, I'll do it again so that you can see what it says, because it'll just make as many copies as you want. And so it says creating a copy in the lower left, and you say show file location, and it'll take you to your drive, which mine is full of things. And this is the copy here. And so I can open that copy, and now I have an editable form of the worksheet. And so that editable form of the worksheet is what you can send out to students. And I think Meredith could talk a little bit about how this integrates into Google Classroom if you use it, but this is a way to copy them and break them up into chunks you can share out either individually or to groups of students. And so I don't know if you want to talk a little bit, Meredith, but I'm going to send you guys the links to the documents you're going to use today.
Yeah, so if you use Google Classroom, you're probably well versed with, creation of assignments and making a copy for each individual student. So you could do it that way, or you could have them be able to view the file and go through the same steps that Kareesa showed, making a copy if they want to work in a group and sharing it out with their group members. If you're using other learning management systems like Schoology or Canvas, there are also similar ways that you can take one document and make a copy for each individual student in an assignment with those as well. So multiple ways in which you can get the document to students.
Cool. And so what I'm going to do right now is I'm copying these links into our chat, and you'll notice that I have the cheat sheet. I just added group 1, and I'm going to add group 2. And what I'm doing with that is we're going to break you guys up in just a second, and we're going to help you. So Dr. Sharada will be in one room. Oh no, I'm sharing it to the wrong person. Okay, sorry. So Dr. Sharada is going to be in one room and I'll be in the other, and we're going to practice making some of these gases. And so that is, so here's group 2. Let me share group 1. And then here is the cheat sheet. And so we're going to do like a breakout 1 and a breakout 2. And so with your breakout room, what you're going to do is you're going to go into those sheets, which should be editable by you. If they're not, I'll change the settings. And in those sheets, you're going to try what the students would be doing. And so you can see on my screen now that there's a student worksheet day 1, and it has a formula here, which is sort of oxygen, nitrogen gases, right? And it's up to you whether you want to show your students the formulas or ask them to guess it. But what we'd like the students to do is fill out the column with the formula for these gases. And then we're going to create a guess structure. And so what that means is that in IQMol, for example, one of the things you can do is you can start a new molecule. So I'm going to do this pretty slowly in a group. So if you want to follow along, you can. And if not, we can talk about it in the individual groups when we break out. So ask me questions as you go. So under File, which I think most of you should be able to find based on the fact you found calculation, what we're going to do is we're going to start a new molecule. And so it says new molecule, or you can do Control-N if you want to know the link shortcut. And it opens up this blank blue screen. And so once you have a blank blue screen, what we're going to do is in our breakout rooms, you guys are going to try to build most of the gases that you have so that you can get practice using IQMol. And so for example, if I want to build water, I might start with clicking on this little element and clicking on oxygen. And then I can plop an oxygen down in the center of this. And then based on the cheat sheet, which I was using before, so if I open up that cheat sheet, I know that I can either continue to add atoms by, so for example, I want to add a hydrogen, right? I can go back over here and I can just add the hydrogen in the same exact way I added the oxygen. Or I can use this little button here, which says that you can add hydrogens to the structure. And so then if you click on this little one, which is the like small like white balls around the center carbon with the plus sign, that one will add however many hydrogens you're missing. And so there's multiple ways to sort of interface with the program that your students might find more or less easy. And so what you're going to do right now in the breakout rooms is we're just going to split up, and I'll message each breakout room, whether you're group 1 or group 2, and you're going to try to write down the formulas for the gases and then make versions. So if you want to split up, like each person makes one gas, or you guys all try to make all of them, and then take a screenshot or a snip or whatever and include it in this second column, where that's what you guess the gas looks like. Because what IQMol does is it takes your guess and it changes the distribution of the electrons, and it changes where the atoms are so that it can find the best version of what you guess. And so the first step is just to make the gases, and we're going to help you make them. We're happy to answer any questions about how to add things in IQMol. And then after that, I'm going to walk you through how to do an optimization, and we'll do that optimization together. So can people access those links? Is it editable to some extent before I break everyone out?
I checked, they are editable.
Okay, perfect. So I'm going to do the breakouts. Let's see. And then, like I said, Dr. Sharada, Meredith, and I will be broken up so that each room has someone who's comfortable with IQMol. Okay.
Kareesa, I'm not sure how the recording works when you go to breakout rooms, about what voices and actions will be recorded. I think it maybe muting the main thing works. I don't know. Usually it's an issue figuring out like what is being recorded in a breakout room.
Okay. If you want, we can do it all together. It's a little more hectic. We could try it in, okay, yeah.
I think we can manage together.
Okay, yeah. Cool. So I think you guys should be invited to join rooms.
Yeah, how did you add a different element? Oh, there it is. Never mind.
Yeah, and a lot of it is just does someone want to do oxygen? We can break it up that way, or we can all do one together. If you want to see it again, I can share my screen with IQMol.
I did water.
Oh, you did water. Great.
How do you do a double bond?
That's a great question. So if you do a double bond, you drag again like you made that bond. And so if you added a carbon, all you got to do is just sort of drag back from the carbon to whatever you connected it to, and it will pop in a second double bond.
See it.
Did that help?
Yeah, we're good.
Okay. And the fun thing about IQMol is if you don't add a double bond, when it does the optimization, it will add it. So if your students don't have the intuition of this should be a double bond, when it optimizes it, it'll bring it closer and it'll pop up as a double bond because it will calculate the occupation of the electrons into those orbitals. So it's kind of cool.
Optimize it.
So we're going to do the optimization together.
Okay.
Yeah, so
So
you're
now I
ahead
should
of
just
the,
take a screenshot of molecule I'm in.
yeah. So in theory, with your students, you could do it sort of either way where you have them sort of work together and create the structures and then explain the optimization, or you can do it all at once where you show them how to make the structures and do the optimization, but it might make it sort of where they don't necessarily fill in the columns the way they're supposed to. I'm going to jump into the other breakout room. It seems like you guys have figured out how to do the worksheet, so I'm going to make sure that they have access.
Cool.
And another one. It's a triple bond, right? Yep.
So I said at the beginning here, I'm the I'm the AP bio teacher. My chemistry's super weak, so if I get some of the chemistry wrong, don't blame me. And we'll take another picture. Oh
I
my
think
God.
that's
You
the
know this
goal of
thing-
the discovery process, you know?
Yeah. I'm sure you've all found this is whenever you go to do something, you get the whole Zoom menus in your way.
Yeah.
Let's see. Well, I better start naming it. Okay. So what is our next one?
CO2.
Okay.
Are you in the group 1 document link? I just want to double check.
Am I?
Yeah. Or are you just like saving the screenshots for right now?
I'm just saving the screenshots and then we're going to add them in.
Okay, makes sense.
Okay. There's the carbon.
As you all saw, you can't just keep clicking in different places. It has to be a click and drag. So IQMol only lets you create bonds. You can break them later on, but you have to start by creating them.
So are we good here? Can I save this one as well?
It's two double bonds there. C
Okay.
has one double bond with oxygen, another with the other.
And it's okay if we don't get them right the first time, because that's part of the reason why IQMol is so cool, because it will fix what you did to a large extent.
I think you can save this.
And the next one is methane, CH4.
Yep.
My lights are turning off.
I can teach a shortcut here once you have the carbon atom.
Okay.
All right. So up there, next to C, there's a button.
after we submit the jobs, but they can get frequencies, they can get the geometry. There's, I mean, just massive amounts of data beyond what I know in chemistry that can come with the files. So yeah, you can go super in depth with it.
And that happens.
That happens after they submit the job, and so you would submit an input file, and then what would come back would be an output file. And we'll see that, I think when we get all back together, we'll see those output files, because we are going to talk about frequencies, obviously, because that relates to molecules, greenhouse gas potential, and what we're going to focus on for day 2 of the lesson.
That's pretty slick.
Yeah.
I'm also going to show you guys some functionality in regards to the bonding, because IQMol can show you specifically where the electrons are located. And so if you're really interested in sort of the fundamental chemistry, you can talk about what makes a pi bond or a double bond different than a single bond. And you can talk about how certain atoms are more electrophilic, and so they have a lot of electrons around them. And you can see that when you look at the orbitals. And so there's all sorts of like kind of nitty gritty stuff you can dig into with IQMol. And you guys are really fast. So I'm giving the other group just a few more minutes to finish, because you guys just like zoomed through it. But if you guys want to, you're also welcome to go back to the main room.
Okay.
Science Olympiad team, and we had this new, well, it's not new, but a protein modeling event I had never looked at before, and it was using another program similar to this.
JMol, right? Yeah, we've used JMol too. It's actually nice to visualize like excited states and things like that. Sorry, what was the molecule again? CCl2F2, right?
So
Here's
help
what,
me out.
here's what you can do. You can have a carbon in there. I'll show you one other thing that we can do. Complete it with hydrogens. With the add hydrogens, yeah. And now when you go back to build, click on Cl2, right? Chlorine. And you can click on 2.
They're just hanging out. I told them they could come back. I think you're on mute.
Okay, cool. Thank you. I broadcasted a message saying when you're finished, just join the main one again.
Perfect.
Because
Yeah,
the other one is kind of moving a little slower and they're talking about it more, and Sharada's having fun, so.
That's fine. I was like, oh, I got the document open and they were like already building molecules, and then they figured on their own how to add the names to them, and I was like, okay, you guys got this.
You're already rocking.
Uh-huh. Yeah.
That's funny.
Yeah.
I think Sharada sent me a document of how to fix that other problem, but I can't see it in the chat anymore, so I might have to wait for her to rejoin before I can sort of respond.
Okay.
Hopefully we can get everybody submitting it, but I need to look at the document and see what the problem was.
Yeah. And I mentioned to the group that I was in that all of the output files were there, that if students weren't able to submit sort of a thing, that it's still doable.
Yeah, which is good. Yeah, your group was just so fast. Like, okay, guys.
Like, whoa.
The other group is doing it where they're making all the structures and then they're going to include the screenshots after. So they're doing everything before they put anything in the document.
Oh, got it.
So it looks like they haven't done anything, but they're just kind of
doing it differently. Yeah.
I was like, are they stuck? And I was like, no, they're working on it. That's cool though. And then I'll open the optimization guide while nobody's here so that we're ready. Okay. We're a little behind schedule.
Yeah,
I'm gonna shut the rooms, maybe.
yeah, I think so.
Plus, I do think the second part's a little easier and a little more kind of explainable, so
Yep.
I think it'll be okay. We just gotta.
Yeah.
They're about to be bumped. Welcome back. Okay, everybody, thanks for rejoining. So the next step for what we're gonna do is, so you've made all these guest structures, and I'm sure you guys realize that sometimes it's a little difficult to make them chemically accurate, and you have this intuition, oh, it could be a double bond, or you don't have the intuition and you're like, I just need to kind of piece these together. And the way that you connect them could be different based on your background knowledge. And then because of that, we're going to get structures that look different. And so I'm not sure if both groups got the chance to submit some of their screenshots. I think group one was kind of doing it as everything as they went. So did you guys manage to get some screenshots in that we could compare, or did I stop you too soon?
I just added screenshots to our file.
Perfect. Okay, cool. I will share my screen and we can talk. I'll show you how you guys did it a little differently, which is good. And something that your students will likely be interested in comparing between groups. And so if you look here, you have, okay, so the comparisons here, you can see you have different zooms and you created some structures that look pretty similar. For example, your CO2, group 2's is a little less bent than group 1's, which is fine. And you have sort of different looking like CFCs. You guys picked different ones, which is totally fine and what we want the students to do. And so now what we're going to do is we're going to let IQMol do all of the quantum chemistry it needs to make these structures chemically accurate. And so in order to do that, we go back to IQMol and you can select any structure. So for example, I have my water showing, but what you do is you go under that calculation and the QChem setup, and depending on what job you had open before, you'll have a different section here. And if the students, for example, opened up a whole brand new IQMol, so I'm going to do that now just so that it looks like what it might for a student.
Kareesa?
Yes.
I want to apologize. I think my group missed one step, which is the energy minimization. I thought that would come next within IQMol,
Okay.
which is why we have the bent CO2 structure, because we didn't do the energy minimization in IQMol before we feed to QChem. Do you mind walking through that?
Yeah, so we can work through that. I don't actually have that as a recommendation for them before they take the screenshots so that students can watch IQMol do it. Because if we use that function, so I'll show you what she's talking about. So in IQMol, there's this E with the like downward arrow in the cheat sheet. And what that does is it does like a rough approximation of an optimization job. And so if you build some structure that looks really strange, so I'm going to try to make a strange looking structure. So say I do this, right? I've kind of made them weird shapes, and then I'll just add a bunch of hydrogens to wherever it wants. This structure isn't necessarily the shape it would be naturally. But if you use this E, the like downward energy, it will try to make it better. And so if your students do that, they might end up with structures that look different from their guesses. And so what we're going to have them do is instead just do a full optimization, which is to go under calculation here with whatever structure you're interested in. And you'll notice that there's these sort of areas filled out, and then there's like, and there's drop down menus on the left. And the one we're interested in is geometry. Sorry, can you guys hear the dogs really loud?
It's fine.
Okay. You can still hear me though? Okay, it's really loud. Okay. So if you, in the folder under day one, there's this file called optimization guide. And let's see, nope, that's the cheat sheet. The optimization guide, and it talks through all these steps. So I'm going to go through these steps, but when you do it with your students, if you need a refresher, this document exists and says everything I'm about to. And what this document says is that to find the best geometry, we use this geometry feature. And then it gives you some inputs that are kind of standard inputs. And I'm happy to talk about it at the end, what we're actually putting in when we click on these things. But what it means is IQMol is doing a bunch of math on our behalf. And that math requires on different equations and approximations to these structures. And so depending on what we select here, it just uses slightly different equations. And I can go into detail about that. And if you want to after this, you can email me and I'll explain it in depth. Because you might have students who are really interested in the math and we can talk about it. But it's not helpful right now. And so after you've changed it to geometry here, and you've made it so that it's kind of our standard variables, which is this 6-31G and B3lib, then we would do that thing where we tried to submit it. And IQMol would, in theory, run the output file. And so Dr. Sharada looked up between the sessions what could potentially fix the issue. And so if you want, we can go through this right now. It might not work. So what we're going to do is everyone, if you can open IQMol, we're going to try to make it so that your jobs will submit. And if this doesn't work, I'm just going to show you what the backup plan is because we already have a backup plan if it doesn't work. So can everybody like thumbs up or something once they've got IQMol open and in front of them? Okay. Got a few thumbs up. Cool. Okay, and so now, if you already have the calculation window open because you were following along, we're just going to close it. And we're going to go up to the top of IQMol again, and you're going to click on calculation, and you'll see this drop down. Before, where we were using QHIM setup, instead, we're going to do edit servers. So can everybody find this and click edit servers here, this last option. It should pop up a window that might look like the one on the left for a Mac or looks like this one for a PC. And then click on the add button, the little green guy in the upper right. And yeah, you get this window. Slightly different, pretty similar. And then let's see. Two possible changes are either to try so it's currently HTTP for me. It might be that for you. You could switch it to the other one. I think, is that, Dr. Sharada, what you were, okay. So you can switch it to the other one. And then we'll click on text connection Where is that, Dr.
I
Sharada?
think that is in the newer version of IQMol. So some of the people who
Okay.
downloaded it recently might be able to see it.
So yeah, if you see a test connection here, click on it. Does that help anyone? Does it say it works or?
I was
So
just
there are-
able to, I was just going to say, I just found the edit server. Could you just go back one step out?
Yes,
That serverless window popped open
this one. Yeah.
and
So now you
yeah,
plus
that one.
the green, the plus button.
Okay.
And now it should
Okay,
pop
I
up like this. Yeah, and then you can change from HTTP to HTTPS.
I think it depends on your local servers which of these might work. So you can have one QChem server set up as HTTP and other set up as HTTPS under two different names, and try which one works.
And then after we do that, you should have two here, I think. Did you have a question? Sorry to interrupt you.
I was just gonna say if that's the only change we do, and then we submit. Okay, I see two. Yes.
Okay, so if we close this now, once you have, so we'll go back to the calculation. Sorry, so I'll do that more slowly. If you go to calculation and then go back to QChem setup, which is where we just were to try to make our optimization file. If you go to this, now in theory, under the server in the lower right-hand corner, you should have QChem, which is what we tried the first time, and the one under it we just made. So if you change it to the one under it and hit submit, we want to see if it works. It didn't work for me. Maybe it works for one of you guys.
When you said click on the one under it, what were you talking about?
Yes, so under the QChem startup, there's a server right above the submit button, and you can turn that into a drop down, which you can click on if you've successfully added it in the last step. Did that work for anybody, or is everyone still? Oh, sorry, there's stuff in the chat I can't see, sorry.
It looks
Yeah,
like
it doesn't seem to be working.
Okay, cool. Okay, so that's completely fine. And the reason that it's fine,
Right?
what?
We have a backup, right?
Yes, I do. So what we've done is we've created in class day one, we made up all of these sample files, which you can share out to your students, which are what would have happened had they submitted it. And we'll continue to figure out what this is. And chances are, if you tried IQMol again in 2 weeks, it might work. It seems like the connection there is a little bit of a daily thing. So just because it didn't work today doesn't mean it wouldn't work on a different day. But this folder, sample files, under in class day one, has the output files in this folder. So what I'm going to do is I'll send you this link. And what you can do is you can download, for example, the oxygen output file, and we can look at it. And so if you download these before your class with your students, if we can't get any of them to work, they can look at these output files in IQMol. And so after you've downloaded it, you can open that output file and we can talk about what it tells us. So I'll share you guys the link. And what I'm going to ask you to do is just look at CO2 for now, because the frequencies that I'm going to talk about in the next couple slides are all based on CO2. So I'm going to share the CO2 folder into the chat, and you guys should all try to download CO2 so that we can look at it. Let's see, chat.
Which of the 3 folders should we open?
So I can tell you, so each of the files, so you guys just made an input file, and that's what you give QChem. The output file has most of the information we talk about, and the checkpoint file has some cool stuff I'm going to talk about at the end. So right now, just download the output file for CO2. Can everybody find it?
Are these found in our third GHG lesson plan? Which folder it's in? Is it in?
Yeah, so it's It's in sample files, which is in class day 1. So it's
Okay.
located with the worksheet
Got it.
that you'd use. And I shared the link to CO2 in the chat if that's easier.
Which of the 3 are we downloading? Oh,
The IMP.
CO2.out.
that out. Got it.
Okay.
See 2 of those.
When I downloaded it, all I have is just a single, I think it's the oxygen atom.
Is there something wrong?
The name of the file in IQMol is CO2 opt freq.
Yeah.
I have 2 of those. I've got a FCHK and then an OUT. Is it the OUT?
Yeah, it's the out. Okay, so the reason you only see a single oxygen is the view it loaded. And so if you use the hand grabber and twist it, it should become visible. Does that help?
Yep.
Okay. Dr. Sharada, could you talk about the energies when people are ready? I need to go grab my computer charger. So just talk about how the geometries change.
Sure.
Okay. And I can let my screen go if you want to. I'll be right back.
Okay, so what IQMol does, it sets up what you think the molecule looks like. Now, of course, the bond distances and the energies is not the same as the real system would be, which is why we take the help of a code like QChem to take that structure and find its minimum energy configuration. So in the output file, when you click on geometries, you will see a few numbers there. When you click on each number, you will see a slight change in the structure. Right? So the bond lengths change a little, the angles change a little, and so on.
Yeah.
So the final structure at the bottom corresponds to the minimum energy structure. And that is when the calculation is complete, the structure is converged, the energy is the minimum energy, the configuration is the minimum energy configuration. And that is a structure we will do further analysis on.
What is that number? Is it an angle? It's energy? What is it?
It is the energy. The unit is in electronic energy, so it's called Hartree. It is about 2600 kilojoule per mole, I think. Yeah. So it's a little high because we're not talking about electronic energy, so it's not very intuitive per se. But you see that number keeps going down and down as you scroll down. So that means that it is trying to find the lowest possible energy.
Cool. And so you'll notice for CO2, my structure was pretty optimized because a lot of my research involves CO2. But if instead you look at this one I downloaded for a CFC on my screen, when you started, I guessed that these bond lengths were really short. And what IQMol did is it stretched them. Because if you guys know about like chlorines and fluorines, they have a lot of electrons and they don't want to be packed really close to the carbon. So our energy is lowered a lot by relaxing those bond lengths. And another thing you can do is if you double click on the word geometries, it gives you the curve of energies that it goes through as it optimizes its structure. So it says that the first couple bond extensions really decrease the energy and make it way more stable. Whereas when you start to get to those final things, it's just sort of fine tuning the length a little bit. And so that's how the program works, is to say, if I move like this, does it get way better or way worse? And if it gets better, it'll keep moving in that direction. And so it just slowly changes the geometry and calculates the energies. And so another thing you'll notice here is that above geometries is the word frequencies. And that's actually the second part of day 2. And so that output is described in the worksheet if you scroll down from where you were looking at. And so we're having the students resubmit the calculation, and rather than using the optimization keyword to run the job, we use the frequencies. And what that means is we not only want to know what the molecule looks like if it's just sitting by itself statically, but we want to see how it moves. And so that's kind of the cool part of IQMol. And so if I click on this CO2 here, when I look under frequencies, which you guys should all be able to do, there's 3 different frequencies and you can click on them. And so if you click on them once, you get these little arrows which show you which ways the movements are. And if you double click on them, your structure starts to move. So can everybody see that? Cool. And so this is where kind of a lot of the cool chemistry happens, in that you can click through the frequencies on your molecules, and those frequencies have associated energies. And so the numbers here, I'm going to go back to my PowerPoint because I not only have these frequencies, but I also have some equations that are helpful. So I'm going to share this PowerPoint, and it should be what you guys would see if you clicked on it in your own structure. And so what we did is we moved on from the first step after we found these optimized structures, and we created these in motion structures. And these in motion structures correspond to what would happen in the atmosphere. And so while in the atmosphere, CO2 can move in all these directions, and it can sort of spin in space and move around. And so your students go from seeing a molecule to seeing a collection of movements caused by the atoms. And each of these symmetries, or each of these frequencies, has a symmetry to it and can be described. And so in our lesson plan, we have this activity that's called symmetry in motion. And I'm going to go through it quickly with you guys because we're a little bit behind schedule. But what it is it's a kinesthetic activity that involves your students and these frequencies. And so this might be a little silly, but what you're going to instruct your students to, or it might feel silly, but what you're going to instruct your students to do is to imagine that their torso is the carbon for CO2. And each of their hands, which you hold out to your side, is oxygens. And you can imagine that if your hands are sort of level with your shoulders, you can move both of them in and out together. And because you're moving in and out together, along the middle of you, there's a line you're symmetric about. So that's called your symmetric stretch. And so CO2 here can do the same thing as you. You can symmetrically stretch with CO2. And so that's one way to teach them about the motion. And then if instead of doing a symmetric stretch, you do an asymmetric stretch. So you put both your hands to the right and then the left at the same time. And now you're asymmetrically stretching. And so that's what CO2 does. And it does it with a certain energy and a certain frequency. And then you can imagine that you're feeling a little crazy. So now you can put your hands up and down. And now relative to you, you're bending your structure. And that's the bend. And we also call it an out of plane bend, because if you started as a plane, you're sort of forcing 2 of your arms out of the plane you started in. So that's another word for it. And these frequencies are the frequencies that catch light. So we're really interested in them. And after we have the students write down all those frequencies in the worksheet you already had, they are then asked to convert what IQMol gives them, which is a wave number. So those numbers you see are in inverse centimeters, which is a little strange if you're not a chemist who's encountered it before. But you can convert that to wavelength, which is far more comfortable. And the conversion for that equation is what they do in their first homework. And so in class, they calculate all these frequencies. You send them home with that worksheet, and you ask them on the homework to calculate the wavelength it corresponds to and to identify which one of them is in the wavelength range of IR that we absorb from the sun. And so I'm going to exit out of this real quick and show you guys the homework, which is in that homework folder. Do you have a question or? Okay. So the homework, which you guys can see on my screen, is basically a big table they fill out where they put in the frequencies they calculate in class. They convert them into wavelengths, and then they identify which ones are in the range of 0.4 to 4.5 micrometers, because that is the wavelength range that we can absorb from the sun. And so we do tell them that that's the range they're looking for. But in addition to having to be in the right range, the stretch that absorbs IR has to be one of our asymmetric stretches. So what we have them do is we highlight the ones that they calculated as being in the wavelength range we like and being asymmetric. Because if you look at this CO2 here, when you, here, I'll present it so that it looks nice. So this asymmetric stretch, our first stretch, it's really tiny, but it's got like 2,000 inverse centimeters, which when we calculate in the homework, we get that to be equal to about 4.4 micrometers, which lies in the range that can be absorbed by sunlight. That range, that specific frequency is what picks up the energy from the light as it passes by CO2. And then it just changes the way that the stretch happens. And so you can imagine if you're the CO2 and you're sort of doing your asymmetric oscillation, the correct energy passes you by and you absorb it, it increases the speed at which you vibrate and it changes how you're moving. So you have all this extra energy now. And for your students, if you imagined doing this activity in a room of them, right? If you have them doing this like slow oscillation and then you tap one on the shoulder, which is they've absorbed a little bit of the IR light, they start to increase their speed. As you continue to tap people's shoulders, the room is going to feel way more crazy. And that increase in energy is like what happens in the atmosphere. You absorb the IR light and you change your frequencies, and the ways that it absorbs it is based on the energy of the original frequency and the type of stretch. And so hopefully you can use examples like this with your students and have the time to work through a few different structures. So for example, the CFC that I had shown you previously here also has its own frequencies. And those frequencies are different than the ones we see for CO2 because it's got different molecules. And so you can see there's different bends caused by the fluorines oscillating together or the chlorines twisting. And so you can see how as you add atoms, these frequencies get really hard to describe, but they're interesting and they depend on what the molecule's made of. And so what we want the students to do is to reflect on the differences in energies, how, for example, if you opened the NO2, so I'm just going to show you, or N2, I'll just show it to you guys. So if we open up the N2, which you guys don't need to, but I'll show you what it is, you only get one frequency. And the reason is that if you hold your hands in front of it, your torso is not involved at all. The only thing you can do with your hands is pull them apart and push them back together. And if you try to sort of move them together, all you're doing is translating it. You're not stretching your structure. So N2 only has one possible stretch. And none of those stretches are asymmetric. So because none of the stretches are asymmetric, and you only have one of them, you can't have N2 absorbing IR light, even though it's in the correct range. So we teach students how you need the combination of the type of stretch, which they learn to identify in the kinesthetic activity, and the energy they calculate. Does anybody have questions about that?
Can you explain the significance of the, like, why is it that the asymmetrics, is it the asymmetry or is it the frequency, frequency of the asymmetry?
So the asymmetry, what's happening when the symmetry of the molecule changes is you change where the dipole moment is oriented. Is dipole moment a comfortable word for everyone? Okay, so what dipole moment means is if, for example, you have a positive here and a negative here, the dipole moment would point in a direction based on those charges. And so when you have CO2, you have two negatives next to a positive. And when you symmetrically stretch it, the dipole moment stays the same because the charges are always located sort of in the same place. But when you asymmetrically stretch it, you change the dipole moment because you're pushing all the negative charge in the same direction. And so that change in dipole is what allows the light, which is a wave, to sort of catch into the frequency, because as the charge moves back and forth, the light can integrate and increase that frequency. So it's also constructive interference, if that's a comfortable word. So the movement of the charge constructively pairs with the incoming light, and it causes it to absorb it. And so it's a little complicated when you get down to the quantum of it, but that's what's happening, is you're moving the charge in a new way. That's a great question. And I also, in some of the guides here that we're not specifically showing, I detail some of that, but it's good to kind of think about it because you will encounter it. And so at the beginning of in-class day 2, we shared out with them the first part. So we've split this into 3 parts because this is kind of the discovery day and sort of figuring out why they're so different, because they do a little bit of differentiating them in the homework with their calculations, but we want them to really think about how that manifests in their greenhouse gas warming potentials, or in their global warming potentials. And so the first thing they do is they work with each other and they compare which ones they identified as IR active. And so if you look at this homework, in theory, they shouldn't have identified O2 or N2 as IR active because they don't have asymmetric stretches. But each of the other ones, in theory, should have 1 or 2 that they think could be IR active. And so then they'll write that down in the worksheet, which you can also make copies of like we did before and share out to them. And then the next part, I think Meredith is going to talk a little bit about as a technique. So I'll show you what this is. So Meredith.
My dog is also barking. It's a dog barking day. Yeah, so this low information experimental figures is something that I had seen in a training a couple of years ago and have been utilizing in my classes, where you give students a graph or some chart or something, but you've eliminated some of the identifiers to it. And in this case, we've eliminated the molecule that this graph is representing. And so the idea is to just have students start to converse about, okay, what is this showing? What am I seeing? What could this be in relation to what we've studied and what we talked about in day 1 of the lesson? And so the idea is just to have them start having those discussions about data, because too often they look at, okay, yeah, this chart says like absorbance and wavelength. Okay, so this is the absorbance of carbon dioxide. They don't actually talk about what the lines represent. And so you give students the 4 spectrum of the molecules and have them either individually write out what molecule they think it is. So this one is CO2, as we can see, and then talk about why did they choose that molecule. So they should be able to provide some background or some reasoning based upon their observations, why they chose this to be representative of CO2. And so there's the 4 that you give them. So they could do this individually. They could look at the graphs with a partner or a group and come up with water, nitrous oxide, methane, and carbon dioxide. And so the premise of it is just to get them to kind of think about, okay, we've talked about frequencies, we've talked about absorbance of the IR, what is this graph showing? And how can I relate it to like the homework that they did?
Yeah, so in the homework, for example, I had you download CO2 so that we could specifically compare it to that spectra. So in the homework, we had 3 frequencies, only one of which we ID'd to be both asymmetric and IR active, which is this 4.4 micrometer frequency. And so when they get into class and they see this, we'd like them to look at this really big peak at about 4.4 micrometers and think, oh, this could be CO2, because there's this peak of absorption here. And the second figure that we have here with this yellow box is something you can recommend to students. The yellow box is the range of wavelengths of IR light from the sun that we can absorb. And so, yeah, there's more data in the figure, but they need to identify this critical range of sunlight and see what peaks are in there and use that to identify their spectra. And we include the 4 which we do in this worksheet because, for example, water, methane, nitrous oxide, and carbon dioxide are all pretty common in the atmosphere. And one of the reasons, and so we want them to be able to look at it. And they might ask, well, why don't you have N2 or O2? Because it's super common. And the reason is there's not a spectra. It doesn't absorb any IR. So we can't look at it. Like you would just have a flat line. So they don't publish that data because scientists are like, well, there's nothing on this picture. And then if they ask why we don't have any of the CFCs, it's because they're sort of industrial coolants and that IR data is really complicated and messy. And so we don't necessarily want to use those as examples, but these 4 kind of allow them to compare the location of the shifts. And so, for example, methane, you can see has a bunch of little lines all close together because the IR absorbing lines in that situation are the hydrogens moving. And since there are so many of them, there's a lot of really close peaks together, which they'll see in their frequency calculation and in this experimental data. Does that make sense?
Anthony had a question in the chat. He said, I'm used to seeing IR spectra from 500 to 4,000. Was there a reason why we went with micrometers instead?
Yeah, so that's a great question. And a lot of chemists do prefer kind of like nanometers. And the reason that we did this is because if you want to, all of these spectra we're taking off of the NIST chemistry website. And so while we gave them the data, you're also welcome to include an assignment where you teach them how to look up this data as a scientist would. And so these are direct snips from the national website, which is a reference they can use to do other research. And so we just wanted to make it familiar and not reformat all the data so that if you want them to do some sort of investigative research into these spectra, you can have them look up, for example, on a homework, a different compound, and the spectra would look very similar to the ones we've shown here. And so we were hoping to just make it so that you could potentially modify this and that it would look like the national websites record. Though it is a little strange feeling as a chemist. Does that help? So we basically tried to make this so that they could be as much of the chemist or the chemical engineer or the environmental scientist as they could be. And if you guys want to modify the activity, we'd love it. And we'd love for them to sort of experience it the way you feel is best. Okay, we got another. Yeah, so NIST is the website this comes from, and they publish pretty often. Here, I can also add that, add the link later to the website, and I think it is in the actual guide, but I'll make sure it's there so that you guys can click on that website and look at it. Cool. And sorry, we're going a little bit over, but so the next thing that we do is, so based on these, what we'd ask the students to do is guess which one they think is most likely to be the worst greenhouse gas. And if you were just looking at absorbance, which one would you ID as being the worst based on these figures? Sorry if it's a really small font. Does anybody have a guess?
Water?
Yes. So that's what we'd like them to guess, because it seems reasonable. Water's good at absorbing IR. And so we want to ask them, so what do you think? And then we share out part 2, the second worksheet. And part 2 has this graph, or this chart they need to fill out, which has the global warming potentials of different gases, and they sort of have to identify what they are based on the hints. Just kind of give them a little bit more engagement and not just sort of give them a table. And so like a lot of students probably get a kick out of like cow farts, which some of you might know is like methane. And so just to add some of that. And so they fill in this chart with either the names or the molecules. And then we ask them to look at it and say, was your answer based on absorbance correct? Does water have the highest global warming potential? And we want them to say, no, it doesn't. So something's not right. Like they're a little confused. And then we have in class day 2 part 3. And that is to say, okay, you're missing something. And what you're missing is atmospheric lifetime information. And it starts with a little story about water that's related to our previous analogy. And so I don't have that here because it's a lot of text. But the idea is that if, for example, you have that room of students you're exciting as they oscillate, right? And they move in different ways. If you have a water molecule, right? If you excite it, it starts to oscillate. It's great at being excited. It might happen that it quickly rains out of the atmosphere. And when that water molecule falls back into the ocean, it takes up that energy. So you lose its ability to heat up the atmosphere. Whereas if you have something like the CFC, which lives for 140 years, if it has a low absorbance, it doesn't matter because it gets excited once and it floats around for like a century, warming the atmosphere. And so we create this connection to lifetimes as the second component of whether something is IR active. And you could change the column that's IR active to strength of IR activity, for example, because we guessed water was the highest IR absorbing, but it turns out that because it only lives, a single molecule only stays in the atmosphere for a day, it's got a really bad global warming potential. Whereas CO2 is able to absorb it fairly similarly to water and can persist for thousands of years. So it causes a lot of global warming. And so you can do this. And one of the questions we ask students is, why does carbon dioxide have a global warming potential of 1? And we ask them that question so that they realize that global warming potentials are calibrated relative to carbon dioxide. And so if the number is less than 1, the molecule is less bad in terms of global warming than CO2. If it's greater than 1, so for example, methane is 21 times worse than CO2 when it comes to global warming. And so this is sort of the learning objective of the AP classes, and we want them to be able to reflect on how we understand molecularly what happens in terms of the moving structures being able to absorb the light. But we can't just consider that molecular state because it also depends if that molecule lasts a long time in the atmosphere. And we sort of have them go through this process of discovery stepwise using the data they develop in the first class. And so that's overall the like arch of the lesson. And we rushed a little bit at the end. We were hoping to work through the last bits a little bit, but we don't want to sort of keep you forever. And then I think Meredith can talk a little bit about one of the ways you can ask students to reflect, but you could certainly develop alternative homework assignments based on this lesson or leading into other lessons.
Yeah, so I don't know how familiar everyone is with a claim evidence reasoning or a CER if you use that in your classroom, but it's a really great way for students to be able to reflect, and in this case, answer our question, why and how do greenhouse gases contribute to global warming? So hopefully after this 2-day lesson, or however many days it takes you in your class structure, they can provide some statement. It could be as specific as carbon dioxide is a greenhouse gas. And they have their evidence from all of that data that they compiled with the frequencies and figuring out which molecules are IR active and the global warming potential. And then they should be able to tie that into previous lessons, potentially on biogeochemical cycles, like how water doesn't last a long time in the atmosphere. And so I call it a claim evidence reasoning 1-pager, and feel free to use this outside of this lesson. You can modify it to change the question or the anchoring phenomenon if you use that in your class. But it just provides a good structure for them to find their claim, their evidence, and then I've broken out reasoning because I always find that students really struggle with that reasoning part. They oftentimes just reiterate their evidence. They don't relate it to some sort of other disciplinary idea, and they don't know how to kind of connect it to other things that they've learned in the class. So you'll see those sentence starters in there underneath of the reasoning to kind of help them figure out, okay, my evidence is showing I know this because of something else I've learned, and I can apply it through this method. So that's kind of how the wrap up of the lesson occurs, is having students complete this one-page claim evidence reasoning, answering that question of why and how do greenhouse gases contribute to global warming. And then just a reminder, if you were using this for AP Environmental Science, this lesson would completely check off and go a little bit above and beyond that topic on 9.3, the greenhouse effect. And you can see they should be able to identify greenhouse gases and identify the sources and potency of those greenhouse gases with that global warming potential. And like I mentioned at the beginning of class, the NGSS alignment is also pretty broad. I just found it to best fit under being able to analyze geoscience, but it obviously fits under physical sciences and looking at energy of molecules as well. So then moving ahead, like I mentioned, if this is in an AP Environmental Science class, you would directly go into topic 9.4, which is all about now the increases of greenhouse gases in the atmosphere. And you could talk to students about or incorporate other activities you have about, okay, what are human activities that input more greenhouse gases into the atmosphere? What are their impacts on the atmosphere, their environment? What are other related environmental problems? You could also look at, okay, what are solutions to greenhouse gases in the atmosphere? Is it renewables? How can we talk about infrastructure and energy efficiency? You could look at, our carbon footprint. Have students calculate what their carbon footprint is. And you can always tie back into population and how population has an impact on the increases of greenhouse gases in the atmosphere.
And so, like I just want to reiterate, so you can access the lesson plan using this link, which is on the Women in Chemical Engineering website and will stay there kind of forever. And in addition, if you look at your folder currently, so if you look in homework 1, for example, you might notice that in homework 1, there's not an answer guide currently. So is that true? Is that what you guys see? You don't see an answer guide? If you look under any of the homeworks? Okay, yeah, so you don't see it. And so the reason you don't see it is because I don't want to make this too easy for your students to Google. And so what I'm going to do is we've collected your email addresses and I'm going to add you in just a few moments to the answer guide folders, which are here, and you just can't see them yet. And so then if you want to share it with other teachers, you can. But you don't have to share it with your students, because if you share it with your students, then they could potentially look ahead in the activity and get the answers. And so that's why we have that format. So once it's added, you'll see it, but we just have that folder restricted to add user only rather than anyone with link can view, because we just want to add that structure. So by the end of today, you'll get an email from me saying you've been added to these answer guide folders. So I just wanted to let you know that exists. And if, for example, you're watching this webinar instead of attending it in person, all you need to do is email me, which is my email listed here, or contact Women in Chemical Engineering at USC, and they can add you to those folders because they have admin access. And so we just want to make it so that sort of anyone can get access to this. And then another thing that's possible is, so we've just kind of given you this really fast version of this lesson plan, but what we can do is we can work with you in the future either to learn more about it, to refine these skills, or if you want to, if you know when you're going to teach this, you can schedule for some USC grad and undergrad students to join you in your lecture and help the students with the troubleshooting and help them with submitting it and sort of teaching them how to use IQMol. And all we need from you in order to do that is sufficient time in advance to make sure we have some volunteers who have been through USC's minor volunteer process, which is sometimes a background check, but sort of we need to be approved to work with you as you guys have sort of students who are minors. So all we need to do is to get an email from you saying, I'd like to plan this maybe in this month. Could you hook me up with 3 to 4 students because I have this class size, or this many students? And then we'll make sure the volunteers are approved and can work with you and help out your students. And if you looked at this program and you're like, wow, I like this lesson plan, but it's not exactly what I want. If I could use it in this chemistry course to do something cool, I would. Then we just ask that you email us. We're happy to work with you to develop lesson plans. We have volunteers in Women in Chemical Engineering who want to do lesson plan development as their outreach. And so if you could benefit from having us help you or to talk more about the program's functionality, we'd love to hear about it. And in particular, I'm going to share this survey into the chat, which we ask you guys to fill out kind of as a post survey. And you can fill it out right now if you'd like to. But if you have any questions or feedback, you're welcome to email me, Women in Chemical Engineering, Dr. Sharada. You can find her online with her website. We're available and happy to chat. And we'd like to acknowledge the efforts by the USC K-12 STEM Center, which is, as Dr. Sharada mentioned earlier, Katie Mills. They help us coordinate these activities for professional development for you and also volunteering in classroom. And so they're the sorts of people who help us get approved to work with you guys and your students. And so if you want to, they have a website that describes a ton more activities that they run regularly your students can participate in. And they also have an Instagram that they wanted us to sort of signal boost. So if you're interested in learning more about them, feel free to follow those resources. And then I know I'm happy to stick around and answer any sort of lingering questions about IQMol. And I know that a few of you were asking about some of the other chemistry stuff it can do. So if you want, I'll give you just like a few-minute breakdown of some of the other cool stuff that I think is really applicable. But if not, and you have things to go to, thank you so much for attending. And like I said, we're going to post this webinar on the Women in Chemical Engineering website, and we can send out the link to you. And it will end up in the folder as well. So it should be like readily available. Share it with any colleagues. Let us know if you need more help. We're happy to sort of continue to build off of this, since this is our sort of first program that we're putting on.
Kareesa, there's a question on chat saying, can you put the survey in the chat?
Oh, yes. Oh, sorry. It keeps trying to private chat people. There you go. You should.
I just wanted to add one thing really quick. So this, like, Kareesa and Meredith got together and put all of this amazing work together in the course of a summer, and they were gracious enough to volunteer this time to help you all out through like how we can potentially use these visualization tools in a classroom. So I'm very grateful to both of them for coming up with such a nice comprehensive lesson plan that aligns with so many standards. And it is also incredible of all of you to show up on a Saturday morning when you're probably already exhausted with a lot of Zoom lectures through the week. So I'm very grateful that you all showed up. I hope this was useful to you. And yeah, we can stick around a little longer for questions, but thank you again for joining us.
And if you're interested in developing your own lesson plan, I will say it took us like approximately 5 hour to hour 15-minute sessions to put the lesson plan together. And then we did future work to sort of make it shareable like we did with this seminar. But if you want to develop your own, it would probably take us around 5 hours to do it. And that's probably less effort because we had to start from scratch in terms of using IQMol, and you guys already have some of that background. So it might be closer to 4 hours to develop a second lesson plan.
And the glitch that we faced today was probably because the QChem's public server was down. I believe you might just be able to use it in a couple of days. If you still have trouble, we can find ways to troubleshoot this. But I think it was just a one-off unfortunate thing that the server didn't work today.
And I just want to reiterate what Dr. Sharada said, that, thank you all for taking time out of your Saturday. As a teacher, I know, we work endless hours, so we all appreciate you coming, and hopefully you can find this useful and use it with your classes. So thanks again.
Thank you all.
So if If you want to, I can show you right now one of the other cool things about IQMol I mentioned in one of the breakout rooms so that you guys can. So in those folders, there's also checkpoint files. And you guys asked like, oh, like which one do we download? And the output files have the geometry optimization, but the checkpoint files will actually show you the molecular orbitals. And so if you're like just interested in AP environmental science, and you really don't want to know too much about the chemistry, it might be less interesting. But if you have sort of a chemical interest in it, for example, you can look at something like CO2 and open the checkpoint. Oh no. Let's see if this one just, okay. Maybe not the CO2 one. I'll make sure there's a functional one uploaded. Let's see, we'll look at methane. This one has some double bonds, so let's.
My CO2 opened.
And it works for the checkpoint?
How do I know if it's working?
Just if it didn't give you an error when you opened it.
No, it's there.
Oh, okay. So you might be able to look at CO2 then. I don't know why my file's weird, but if you open up kind of the drop down we were looking at before, you'll notice that surfaces now has an arrow next to it, which it didn't before. And you can open up the arrow under surfaces here, where before we only had so surfaces didn't have an arrow, we just had frequencies and geometries. When you open a checkpoint file, these things called canonical orbitals appear. And if you click on the canonical orbitals, it gives you the option to map out all of the orbitals on this. And if orbital is a strange word, it basically just means the shapes of the electrons, clouds that around these molecules. And so if, for example, we map out so I did alpha 1 to alpha 12, which just means I want the smallest orbitals to the last one that doesn't have any electrons. So if you see here on the right, there's this little kind of like climbing ladder here. And you'll notice that once you get to this line, you stop having circles. And what that means is that these are empty orbitals. So all of the electrons lie in the bottom portion of this graph. So we only need to calculate from 1 to 12, because 12 is sort of the first empty orbital. And so when we hit calculate, it does all this math for us. And what it's doing is it's going to specifically show us where the electrons are likely to be. That's fun.
That's odd.
Yeah, let's see.
Why didn't you just do the HOMO or something? Oh, it's showing the s orbitals, I think.
Yeah, but it's not mapping them onto the structure very well. It's being a little silly. Let me open another one. Asked IQMol to do too many things today. So water has even less. It just has 6. Okay, yeah, so water looks okay now. So as you can see here, the lowest occupied molecular orbital is an S-type orbital on oxygen for water. And the second one is this sort of big cloud of electron charge, which you can see on my screen. And when it looks like this, that's what a sigma bond looks like. And so that's a single bond. And what it means is that, I don't know, are you guys comfortable with s orbitals, or is that, okay. So if you have 2 s orbitals, as you move them closer together, they form this round cloud because you have electrons that are all the same interacting in this cloud. And so our first molecular orbital that we're showing here is that cloud around H2O. And it represents both sigma bonds between the hydrogen and the oxygen. And so when we go to alpha 3, you get this sort of split structure. And what that is it's still just the 2 sigma bonds, but they're not interacting with each other. And so you have an s orbital on oxygen and an s orbital on one of the hydrogens forming a sigma bond. And then you have a different s orbital on oxygen forming a sigma bond with the other s orbital on hydrogen. And so now they're just split. So it's not anti-bonding or anything, if that's a comfortable language. They're still just basic sigma bonds. that you're stacking. And then here you have both sigma bond between oxygen and the hydrogens and a lone pair on oxygen. And so if you teach your students in chemistry about why there are like tetrahedron shapes or why something with a nitrogen in it might be bent, you can have them visualize the lone pairs using these checkpoint files. And so you can see how there's all this charge that's sort of sticking out past the oxygen, and that represents the lone pair on oxygen. And then if you look at the LUMO, it also has where there's so much sort of charge on oxygen that it's also sticking out of the plane for this. And so you can talk about where the extra charge on the oxygen ends up around the structure and how it relates to it. So let me see if I can download the CO2 one and see if it actually works, because CO2 is pretty interesting and I can tell you about double bonds. So let me just see if I can see if that one actually works or if there's a problem. I don't know if one of you's already looked at CO2 from the files. Let's see, download. And so the only thing that our checkpoint files show us are these orbitals. And so if you want to talk to your students about those orbitals, you're welcome to. We just don't specifically tell you to download this because it is sort of a special interest case that doesn't necessarily directly connect to what we talk about. One second, sorry, this is too many tabs. And the little zoom bar. And so if we were to design a chemistry lesson plan, I think one that would be particularly cool is teaching them how to do some of the like Vesper labels that you do and teach them about how different groups interact and how that changes the types of bonds they make. And so I do think there's a lot of potential there. And another thing that we didn't talk about in this lesson plan is our ability to make reaction coordinates. And so you show them those pictures, you know, where you have a reactant on one side, a hill, and then a product on the other side. And you calculate the difference in energy between the top of the hill and your reactant to calculate your activation energy. And we can do every step of that process in IQMol, and they could calculate the barriers of some of your reactions. And so we don't use that calculation here because it takes a little longer. But if you wanted to develop a lesson plan where they work through the steps of a chemical process, such as an SN2 reaction or something simple where you're swapping out a functional group, we can do that in IQMol. And so let's see if this one works better. So if you guys have any questions about that, I'm happy to talk about it. With Meredith, the first time we did go through making a reaction coordinate, but we decided not to incorporate that into our first lesson plan. So that's why it's not in this one. And you guys are welcome to leave or ask me questions to get me talking about something else because I can talk for a while. So for example here, once again, you have s orbitals on the oxygens as your lowest energy orbitals, so like the first occupied. And then the second one is the same thing. It's just different s orbitals because there's a lot of electrons on the oxygens. The next one is an s orbital on carbon. And so some of these lower ones are less interesting to us as chemists because we expect them, but your students might be like, wow, I can actually see the charge. You know, I know what an s orbital looks like. And then when you start to combine them, you get orbitals that look like this, which is your sigma bond orbitals across the structure. And then I think the next one is sigma bond 2. Yeah. So this is like we saw in water. It's just a split sigma bond, but both the carbons and oxygens are interacting, and then the other carbons and oxygens are interacting. So this is just more sigma bonds. And you can think about it as each of these is like half of the sigma bonding character. And so since we have a sigma bond on one side and a sigma bond on the other side, we'd expect to see 2 sigma bonding orbitals, and we do, which is kind of cool. But that's a little complicated. And then this one, for example, it looks like oxygen lone pairs because of how much sort of charges out to the end, but you also do have a little bit of sigma bonding character in the middle here, but it's a little blurrier. Let's see if we can, so this is another, okay, cool. We found our first pi bond. So because our p orbitals are shaped like dumbbells, you know, we talk about, oh, look at the dumbbells. When you have two dumbbells that you bring closer together, they form the sphere of charge on top of and below the molecule. And that shows up as this sort of like split thing where you have what looks like a sigma bond, but it's popped out of the plane. So the bond itself isn't included, the drawn bond, because that bond takes place further from these atoms because of the original shape of the p orbital. And then because we can rotate CO2, we have them in different directions, because you can imagine your dumbbells would be sticking off at sort of cross angles. And so because of that, we see pi bonds that stick out at different angles. And then this one looks like lone pair because of how much charge there is. Let's see what we got. Okay, this is an anti-bonding pi orbital, if that's comfortable. And so if you have your dumbbells, but you have, instead of having both of the negatives in the dumbbell on top, if you flip one over, now you've got this like twisty pattern. And so you can use this to teach them some advanced like chemical bonding if you're teaching an APES class, or you know a teacher who would want to teach something about this program. And so you can use it to show them. So the reason why CO2 has a double bond is because of these pi bonds, not just at the sigma bonds. And that relates to the number of electrons. And so you can have them write like electronic configurations and talk about how many electrons there are. So there's a lot of connections to what you talk about in high school chemistry to sort of the basics of what this program does. So that's something I just wanted to show you because I think it's pretty cool. And I think a chemistry teacher could be interested in doing something like this. Does anybody have any questions?
Does it give any data on like bond angles?
Yes, that's excellent. Okay, so I'm going to switch back to the output file because sometimes they're more helpful. So if you open the output file, and so you can have your students do this with their output files if you want to, you can click on using the select tool. If I select just one, at the bottom left, which is kind of hard to see on my screen, it says O atom. So if you click on something here, let me see if I can make this bigger. So you see here in this little lower corner, there's like a tiny bit of gray writing. You can click on, that identifies it. Now, if you hit Control or whatever the Mac equivalent is, and you click on another atom, or no, I guess you can just click on the atom. Okay, yeah, just click on another one. You don't need to do Control. It will tell you the bond length. So if you click on two different atoms using the select tool, it gives you the bond length. If you click on 3, it will tell you the bond angle. And so for CO2, it's close to 180. But if you wanted to, you could compare CO2 and water and have them talk about why the lone pair is important in that interaction. And so there's a lot of stuff that you can do. And then if you click on 4, it shows you torsion, which is a little tricky, but it just means that if you have 3 connected, and for example, if we put a hydrogen on this one, right? It's not gonna like me. It doesn't want to do it. Okay. If you then click on 4, you can imagine rotating this hydrogen around the carbon. And as you change that angle, it changes the torsion. So the torsion is just one step higher. And it's not something you talk about in high school, but it just relates to sort of the fact we're in a 3D space and we know more than just the angle. I think someone had a question in the chat. Okay, thank you for coming, the person who's signing off. Hopefully you learned some cool things. So yeah, there is extra functionality here.